How are you guys today? Hoping you can hear my voice.
Yes, miss.
So for today, we're going to start a new topic. It was concrete staircase design. I'm not sure whether it's already uploaded inside the column or not. But if it's not uploaded yet, I can share the notes with you. I have shared a note in the WhatsApp group. You can refer to the notes or the reinforced concrete staircase design. I mentioned before, actually, we're supposed to cover staircase design before column design. Because staircase design is the course objective number. So in your final exam question number 2 will be staircase design. The last question will be column design. But because for the project staircase is a group calculation, whereas for the column it is an individual calculation. That's why I covered the column topic first, so that you have more time to do your calculation for your project. For staircase, you can design it as a group, and the staircase design is simple compared to column calculation. Okay. So basically, at the end of our lesson, you should be able to identify type of staircase and define and explain loading arrangement and method of analysis. And loading calculation and analysis to calculate the moment and shift form of the staircase. Draw shear force and moment diagram and define the staircase. So basically, staircase or stairs are structure that connect two different level or floor vertically. Okay, so usually it will consist numbers of steps, and sometimes if the upper floor is very high, they will be intermediate, and so that you can basically rest a few steps before you continue with stairs on the stage. Okay. So the dimension of the stair actually, when you design, must be able to provide compass to the users. And usually the riser, the height of the stairs, is not more than 180 meters for the public building. For home, residential, private building, can go up to 100 meters. Okay. These are some examples of the staircase. We have spiral, L stair, helical, stepper stairs, and so on. The, the only important thing that we have to note for staircase design is the location of the support of the staircase. Depending on the support or boundary condition of the staircase, the method of design might be simple or a little bit complicated. So we have to know how the staircase is going to be supported. Basically, usually you decide on your own how it's going to be supported. Otherwise, mention inside the architecture layout. If not mentioned, then you can decide where you want to put the support and then design according to that. So these are some examples of reinforced concrete staircase. We have straight staircase, window staircase. Window is when you do not have any landing. Instead, you have a few more steps at the landing there. Okay, so this is what we call window staircase. Then we have two-quarter window, two-quarter landing, quarter landing. Then we have double window, half landing, curved staircase, and also spiral staircase. Okay, so this means that you have more steps. It's not actually landing where you don't have any steps on the landing. So in 3D view, first one is the straight. First one and second one is the straight staircase, and then we have curved staircase on number 3. We have a quarter L-shaped staircase at number 5. This is window staircase, and then half landing, number 6. Okay, half landing. So before we can begin our design, there are few things that you have to know so that you can calculate the loading on the staircase. For example, going or G is the width of the steps. Then we have riser or rise, which is the height of the steps. And then we have the H of the height of the waist. We call the height of the waist or thickness of the waist. So this is the height of the stairs without the going and rising. Then we have the height of the landing. Okay. So going, riser, waist, then landing. So in architectural part, we have lots of other finishes that we can include on the staircase. For example, we have for the staircase. We can have the drag and going is the same thing. We have newel post here, landing newel, and then over the post handrail and so on. Friends, this is just finishes. Okay, it's not part of the reinforced concrete design. Once we finish our reinforced concrete design and casting, we can use this as architectural finishes. Okay, so these are all the part of finishes that we can include on the staircase. So in terms of design, basically the reinforced concrete stair design is similar to concrete slab design. More or less similar. Unless we have it differently, but most or less it's basically similar. In which we design for B equal to 1000 mm. Okay. So in our design, we will calculate the loading action, and then we're going to determine the bending moment and shear force. We have an equation for this, and then effective span based on the layout view of the staircase. Okay, so it is important for you to view the plan view or elevation view of the staircase so that it can help you in terms of design. So in terms of procedure of the design, first we have to determine the average thickness Y and T so that we can calculate the weight of the staircase, and then we calculate the loading on the staircase, and then we calculate the bending moment and shear force. Based on the bending moment value, we're going to design for the reinforcement. Based on the shear force value, we're going to check for the shear, and then we're going to do checking for the deflection and cracking. And last is to sketch the arrangements of reinforcement. The procedure is more or less similar to slab design. In fact, even for the determinations of the concrete nominal cover, we refer to the table for slab design. Okay. So let's go through example that we have in the module textbook. Okay. Example 3.1, stair with landing and continuous at one end. The reinforced concrete staircase for office use is shown in figure example 3.1. It is connected to a landing at the upper part and supported by a beam at the end of the landing. So here is the landing and there's a beam here supporting the landing. At the lower end, the stair is supported by a beam and continuous with the floor slab. So this is the beam supporting the staircase, and then after that there's some slab after the beam. Okay. Design the staircase by using concrete grade 30 and strength of reinforcement of 500 Newton per meter square. The imposed load is 4.0 Newton per meter square and finishes is 0.5 kilonewton. 0.5 kilonewton per meter square. So concrete nominal cover is taken as 25 mm. The width of staircase is 2,500 mm. Width staircase. This width here. 1,500 mm. Thickness of the landing is 150 mm and the thickness of the waist is also 150 mm. Landing waist, the thickness is 150 mm. Design the reinforcement for the stairs. Use diameter bar 10 mm. Okay. In the figure is also given the span of the landing is 1.4 meter. 250 mm this is going. 170 is what we call as riser. Okay, based on the information expected from the figure. Okay, so these are all the specifications given. So width of the staircase is not clear. Width of the staircase meaning the staircase width to the side is 1,500 mm. Lebar staircase. Okay. So like I mentioned just now, for concrete nominal cover, method of calculation is similar to the concrete nominal cover for slab design. Okay, for C minimum due to the bond, C minimum due to the durability, and C minimum due to the solid distance, we use the same table for slab design. Okay, so once you have calculated concrete nominal cover, for this case, the concrete nominal cover is given. This is kilonewton per meter square. This is just of the staircase, but for our design, B is equal to 1,000 mm. Okay. So first, average thickness of the flight. This one you have to memorize the formula, the equation. Y equal to H waist times G square plus R square over root 8 divided by, okay, so we get 181.4 millimeter. Average thickness is equal to Y plus R divided by 2. Okay, so these two equations you have to memorize. It's basically based on this stairs. So we get 266.4 mm. So 266.4 is used to calculate the step weight of the staircase. Okay. So action. So we have both landing and also flight. So first, for landing, slab set weight is equal to thickness of the landing multiplied with concrete density. So we get 3.75 plus finishes 0.5. We get total 4.25. Okay. So variation given is 4. So 1.35 GK plus 1.5 QK, we get 11.74 kilonewton per meter square for landing. Then we calculate flight. The part where we have steps on the staircase. Okay. So 0.266 here is based on the P value that we calculated earlier. Convert it to become meter. So we multiply with concrete density 25. We get 6.65 kilonewton per meter square. Plus finishes, so we get 7.15. 1.35 GK plus 1.5 QK, we get total 15.65 kilonewton per meter square. So we have two different loading on the staircase. One is for the flight, another one is for the landing. Okay, so the flight span based on the figure here. The flight from the middle of the beam until here is 2,500, and then the width of the landing is 1.4 until middle of the beam here. Okay, so write down the value here. 2.5 meter is for the flight, 15.65 kilonewton per meter. Consider 1 meter width. That's why instead of kilonewton per meter square, now it's become kilonewton per meter because we consider 1 meter width for our flight. And for the landing, 11.74 kilonewton per meter. Okay, so total loading, total load on the span is F equal to 15.65 times 2.5 plus 11.74 times 1.4. So total loading on the staircase is 55.56 kilonewton. When we want to calculate design moment, it will become F times L divided by 10. This is the equation that we use for calculating or estimating the moment for the staircase. The equation is fixed value. It's a fixed formula. Okay? Regardless of numbers of steps on the staircase. Okay? So MPP is equal to F times L. L here is total F. Total span. Okay? 55.56 times total span, which is 3.9, divided by 10, we get 21.67 Newton meter. And then in terms of bending moment diagram, we refer back to our staircase. After support, this is our support, we have two beams here. After the support, if there is slab after the support, we consider it as continuous. Meaning at the support, the slab is continuous because the reinforcement from the staircase can go into the slab. So it's considered as continuous. If there is continuous, meaning there's a moment there at the support. So for our case, there will be moment at the support and midspan. And all the moment values are the same, which is 21.67 kilonewton meter. So why is the value like this? Basically, this is the method recommended by design guideline. Use this formula. It is based on best practice of the engineers, because the staircase is not really horizontal. Staircase is actually partially, it's an incline calculation. So we determine and if we approximate the value based on this best practice equation, and this is how we determine our design moment. Okay, so it's based on the equation F times L divided by N. Okay, so now that we have our moment, we can design our main reinforcement. So similarly, like flat design, H is D is determined by using H minus C nominal minus diameter bar divided by 2. So we get 120 mm. Then calculate K. D is 1000. Here. Calculate K, we get K is 0.05, which is lower than K million, so population reinforcement is not required. And then we calculate Z. Z here we get 0.953, so it's 0.953. And then AF required, we get 436.98 millimeter square per meter. Okay. All the calculation that we get is millimeter square per meter. So add this in your next. Okay. So then we calculate AF minimum and AF maximum, similar equation like flat design. Only difference is that we use equal to 1000 millimeter. Okay. So AF minimum we get 181.2 millimeter square per meter, and AF maximum we get 6000 millimeter square per meter. Based on the AS required, we can provide main reinforcement equal with the level 1 here, millimeter square per meter. H10 175 is provided, in which AS provided is 449 millimeter square per meter. Okay. For secondary bar, before you provide the secondary bar, compare AS minimum with 20% of AS provided for main reinforcement here. Okay, AS provided. So we provide 449, 20% from 449 is 89.8, okay, which is lower than AS minimum. So we provide secondary bar based on AS minimum. Okay, based on AS minimum. This 175 lower than AS minimum, cannot provide this one. H10 400 AS provided using 400, AS provided is 196.3 millimeter square per meter, which is larger than AS minimum. Okay, so that is for our main reinforcement design. Then for shear design, the method of calculation estimating the shear force value is similar to the one you have done for your moment distribution method cut section. Kan? Okay. So we have moment 21.67 kilometer, 21.67 kilometer. So summations of moment at A equal to 0, then you get RT. Fy equal to 0, then you get RA. From here, RA is 29.54 kilometer, whereas RB is 26.02 kilometer. So the larger value will be our okay. The larger value will be our. So we calculate A, which is we get larger than 2.0, so this is 2.0. Row L, area of C provided 449 divided by 2 times 3, we get 0.0037, use this value. Then calculate BRTC and minimum, so we get BRTC is 64.24 kilometer, whereas B minimum is 65.07 kilometer. So compare this with the BB, so our BB is lower than BRTC value, therefore checking for shear pass. Okay. Next is for the deflection part. So AS required divided by B times P is 0.0036. Rho naught we get 0.0055. So rho naught is larger than rho. We use the first equation. From our bending moment diagram here, we have two moments at the support. So in this case, K, this is what we consider as the real strength. K equal to 1.5. If T supported, there's no moment at the support. So this is simply supported. K equal to 1.0. If you only have one moment at the support, so this is what we call end strength. K will be 1.3. So for deflection check, you will have only 3 cases. Either integral span when you have 2 moments at the support. If you only have 1 moment at the support, then this is considered as end span. If there is no moment at support is equal to 0, then this is supported beam, is supported staircase. So K is equal to 1.0. So for our case, K is equal to 1.5. So calculate L over D basic. We get 43.5. And modification factor for span, our span is 3.9 meter, which is more than 7 meters. There's no factor for the span. We only have to consider for the S provided divided by S required, which is 1.03. So L over D longer, we get 44.81. L over D actual, 3,900 divided by 120, we get 32.5. Lower than L over D longer, so our checking for deflection pass. Okay. Then for cracking, slab thickness is 150 mm, which is lower than 200 mm. So for mere reinforcement, 3H or 400, whichever lesser. So we get 3H is equal to 3H is equal to 450. So use 400 as maximum spacing. Actual bar spacing provided is 175, which is lower than maximum spacing, so okay. For secondary bar, 3.5 gauge is 5 5 mm, which is larger than 450 mm, so use 450 mm. Actual spacing provided was 400 mm, which is lower than maximum spacing. So checking for secondary bar also. So last is to draw the arrangements of the reinforcement. So first, we have one moment at the span. So this is our reinforcement at the span. 0, 1 bottom, based on the moment at the span. Then we have moment at the support. So we have reinforcement at the support. 0, 3, 0, 2, and here as well. 0, 2. Okay. So 1 and 2 is based on the reinforcement design. And then we have secondary bar 400. This is secondary bar, okay. So secondary bar is the one that you draw causing this reinforcement. Okay, like slab design, we still have to provide something like this for our main reinforcement. Okay, so if you can see the dotted there, that dotted is actually the cross section for the transverse bar. So that is the secondary bar for the reinforcement. Okay, so we draw both, and then the reinforcement at the top part continue up to 1/3 of the total span of the flight. Okay, and as we can see, this reinforcement will go into the other slab beyond the support. So it's considered continuous. Okay, so that is for the first example. Anything that you would like to ask regarding the first example? If there is no question, let's try the one example here as our tutorial, one problem here as our tutorial. Okay, so we're going to design figure 1 here as our tutorial. So, two longitudinal straight reinforced concrete stairs supported by reinforced concrete beams at both ends are shown in figure 1 and 2. Landing slab at both ends of the stairs are monolithically connected to the stairs, so it's continuous. You are required to design the stair in figure, going to design only in figure 1. Figure 2 is basically similar like the one in the example, only that is not continuous. After beam, there is no slab, so it's not continuous. It's only continuous on one support. Okay, so using the following data, unit weight of concrete F25 kg per meter cube, FCK 30, FYK 500, diameter bar is 8 mm, C nominal 25, permanent load 1.0, variable load 4.0. So given riser is 175 mm, Going is 250 mm. H is the height or thickness of the landing, and also the waist is 110 mm. So B is the B of the B, width of the B, okay, which is 260 mm. Okay. So based on the information given, we will have to design for our staircase. So number of steps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times going 250, we get 2500 plus half of the beam width. So we get total span of the flight is 2760 mm. So the span is equal to 2760 mm. Okay. Going, we have number of steps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So number of steps is 10. Multiply with the going, we get 2500 plus width of the beam divided by 2 on both side, upper and lower flight. So we get 2760 mm. That is the span of the. So copy the information first, and we're going to do this as our tutorial. Okay, so first we're going to calculate average thickness. Average thickness y equal to 110 times going square plus riser square. I will root this divided by going. So y value what we got? mm. 134.3 plus riser divided by 2, 175 divided by 2. Get 221.8 millimeter. Now we can calculate the loading action. So for our case, we only have flights, there's no landing. So set weight of the flight will be 0.222 times concrete density plus inches 1.0, get total. And UK given is 4.0. Self weight, what do you get? 5.55 kilonewton per meter square. So add this together, we get 6.55 kilonewton per meter square. So 1.35 GK plus 1.5 UK. What do you get? 14.84 kilonewton per meter square. So ND multiply with 1 meter, so we get 14.84 kilonewton per meter. Now that we have the calculate the action, we can calculate the moment on the span analysis. So for this question that we're doing, figure 1, after the support, there is a slab for upper and lower landing. Okay? So basically, there's a moment here, there's a moment here also. Okay? It's actually similar to our example. So for analysis, (14.84 kilonewton per meter) and is 2.76 meter. A, B. And then we have a bending moment diagram. Okay, so for our MED, the value will be WDL square divided by 10. The equation will be WL square divided by 10. So 14.84 times 2.76 square divided by 10. What you get for the moment value? So we get 11.3 kilonewton meter. And then for bending moment, we have moment here, 11.3 kilonewton meter, 11.3 kilonewton meter. So summation of moment at A equal to 0, 11.3 negative, which clockwise is positive, plus 14.8 times 2.76, distance is 2.76 divided by 2, plus 11.3 minus VA times 2.76. Sorry, VB minus VB times 2.76 equal to 0. So, what is the VB value? It is 14.84. 14.84 times 2.76 times 2.76 divided by 2, or 2.84 times 2.76. So we get GB equal to 20.48. Dimensions of Fy equal to 0. We get dA is also 20.48 kilonewton. Okay, same value. So done the analysis part for the calculation moment and shear force. So based on this moment and shear force value, we can do the reinforcement calculation and shear force check. So then for the reinforcement, then check for shear.
kalau ibu tunggu handphone mana komen? Kat mana nak komen? Komen apa? Kat Google. Google tu kat handphone kan? Google Meet. Dekat mana nak komen nak komen? Tengok kat handphone. Boleh lah. Adalah gambar video. Buku awak ni lama mesej je. Masuk lagi. Ni. Bila pakai ni. Dia pakai tu. Saya dah ambil lah. Dia why?
What is the effective depth value?
Ini Mana saya nak terima?
See?
Google Meet.
Okay. Based on your calculation, what do you get? Okay. Zero point zero. Nine, which is lower than K valence. So it is singly reinforced. Z. Zero point 0.93B, which is lower than 0.95B, so use 0.93B for the calculation. Based on your calculation, AS required, what do you get? $344.84 millimeter square per meter. Calculate AS minimum and AS. Okay. So based on the AS required, what do you want to propose? H8? What is the spacing that you want to propose? H8 125 area provided for 0. 20% from AS provided. 0.2 times 402 is 18.4. For secondary bar, for secondary bar we can provide H8 300, AS provided 168 millimeter square per meter. So done for reinforcement. Now we're going to check for the shear. So for K value, what do you get? 200 divided by D. Power root 8 plus 1.
Dah lah.
For row N, as provided 402 divided by 2 times 0.05 is lower than 0.02. Calculate the RPCN to be minimum.
Maybe. Wait.
What do you get for BRDC? Five, 1, 2. For B minimum, for 3.1. So this value is larger than 20.48. Therefore, checking for shear, pass. Okay. So next we check for the deflection. So rho AS required divided by B times 3, what do you get? 0.00. Or 3, which is lower than rho naught. Okay. We use the first equation. K because we have movement and both support, so our K is 1.5. Calculate L over D basic.
Tengok.
1.5 7 plus 8.72 plus 1.75. So what do you get for L over D basic? That's 51.16. So AS provided divided by AS required. M bagi
Batang tu apa? Dia macam surat cakap tu. Ha? Kau boleh cabut? Kalau cabut tak nak buat ni. Semalam aku buka dekat dia. Dia pasal bulan ni ada jogan kan?
L over D lower we get 36.46. L over D actual 760 divided by 81. What do you get? 34.07. So lower than L over D. Now so check for detection. Fast. Next is to check for the tracking. maximum spacing for the main reinforcement, 3H we get 330, which is lower than 400. So maximum spacing for the head is 330. Actual spacing provided, actual spacing just now, 125. Lower than F maximum. So checking cracking for main reinforcement, pass. For secondary bar, 0.5H or 450 mm, whichever lesser. So 3.5 times 110, we get 385 millimeters, which is lower than 450 mm, so use this one. As actual provided is 300 mm, which is lower than maximum spacing. So again, okay. So checking for cracking for both the main reinforcement and secondary bar, but last is to sketch the arrangements of the reinforcement. You can try to sketch it first.
Sakit mata lah. Cik, sedih saya.
Aduh, aku macam mangga lagi.
Sedih saya bosan. Explain Syah ni. Cik. Cik, sedih mana?
First draw at the midspan. One is 815. And then 2. Then we draw the secondary bar. done for the tutorial of the one flight staircase design. Do you have any question for this tutorial? For the staircase design, any question?
What does spinner mean? S-P-I-N-E-R.
Bahagian tulang belakang kot. Spinal. S-P-I-N-A-L.
So, because we have some time, let's try the one for figure 2. Okay, figure 2. For figure 2, basically we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 steps. We have 1500. The landing span is not given to us, so I give you some value for the landing span. So say 1.5 meter. Okay. So plus this. Okay. From the beam to the landing, it's 260 divided by 2 plus 2500, so 2630 mm. And then for landing, 1500 plus 660 divided by 2, so this will be 1630 mm. Okay. Because B is 260, so we have to plus B divided by 2. The rest of the specification is the same. The only thing is that we have moment here that at the lower part of the staircase, there's no moment at the support. Okay. After the beam, there is no slab, so it's not continuous after the beam. So using the same specification given like previous, average thickness, similar average thickness that we have calculated before, Y and T. What do you get for previous calculation for Y value? I cannot remember. This is 221.8 mm. So 134.3 mm. It's basically similar to previous calculation. And then for action, we have both for flight. Flight is the same value that we calculated before. So ND for flight km/meter square. So WD is 14.484 km/meter. For landing, we have to calculate new one. Safe weight of the landing 0.11 times 25 plus finishes. So QK is 4.0. Zero point 0.11 times 25, what do we get? 2.75 plus finishes 1.0, we get 3.75. What is the ND value? So for analysis part, so we have 14.84 kilonewton per meter and also 11.06 kilonewton per meter. So this is 2630 mm, 1620 mm. So basically we are doing figure 2 now. All the specification is the same like previous calculation for the slide. So we get 24.31 kilonewton meter. Then for moment calculation, for shear force calculation, we only have moment on one direction only. So 24.3 24.31 kilonewton meter. So summations of moment at A equal to 0. So clockwise positive, negative 24.31 plus 14.84 times 2.63 times 2.63 divided by 2 plus 11.06 times 1.6. times 1.63 times 1.6 divided by 2 plus 2.63 minus BB times 4.26 equal to 0. So BB equal to 0.148, which is lower than K valence. This reinforce. Z 0.85D, which is lower than 0.95. As required, we get 811.7 millimeter square per meter. So based on the table here, we can provide H850, which area of steel provided is 1010 millimeter square per meter. So 20% of the as provided is equal equal to 202 millimeters square per meter. So for secondary bar, provide H8 secondary bar, we have to provide H8 200. Area of slip provided will be 252 millimeters square per meter. Then for the main reinforcement, then we have to check for the shear. So BD was 36.14 kilonewton. So that is the larger shear force value. A, K, L, C, okay. So for the shear checking, deflection check, cracking check, and last to sketch the detailing, that will be your homework. So we will check it next class. For deflection, because you only have moment at only at one of the support, K is equal to 1.3, okay? K is equal to 1.3. So I suspect that it will fail in terms of deflection, but you can check first. So if the deflection check fail, and you cannot basically if the deflection check fail, propose what? Okay, propose what? So that deflection check pass. Okay. Then check for the cracking and also draw the detailing. Okay. So that's all for today class. Please write down your IT number for attendance today. If you have any question, you can ask as well. If not, you can leave after you write down your IT number.